Welcome back to the lab, everyone. So glad you're here for this explainer, brought to you by Forge College. Today, we're getting our hands dirty with some absolutely crucial Ethereum fundamentals. You know, we've spent plenty of time observing abstract opcodes and calculating their theoretical costs. But today we move from theory to action. We're running practical optimization drills to really internalize those opcode efficiency trade-offs.
Okay, let's set the stage. Yesterday, we were practically sipping piña coladas on the beach, smoothly scaffolding a breezy Solana cloud project. It was fast, it was light, right? Well, wipe off that sunscreen and put your lab coats back on because we are descending into the deep, scientific, and honestly sometimes unforgiving trenches of Ethereum gas mechanics.
So here's the scientific method for today's lab experiment. We've got welcome to the lab, the SLOAD and SSTORE tools, setting up the environment, before and after code, measuring gas data, and finally, next steps. Let's get right into it.
Section 1. Welcome to the lab. The main goal here is translating all that opcode efficiency analysis we've learned into actual practice, using a guided reproducible script environment. The absolute foundation of this practice is what we call measurement discipline. Basically, we're transitioning from just staring at abstract opcodes on a screen to applying repeatable, measurable optimization moves. I mean, you can't just look at a piece of Solidity code and guess that it's cheaper. No way. You have to isolate the targeted source-level optimizations and then verify their impact deterministically. Really, that is how you become a top-tier smart contract engineer.
Moving on to Section 2, the SLOAD and STORE tools. Brace yourselves, because we're about to analyze the two most notorious gas-guzzling opcodes on the entire Ethereum network.
Think of SLOAD and SSTORE like heavy, incredibly expensive toll booths. Literally, every single time you read from Ethereum state storage, you pay the SLOAD toll. Every time you write to it, boom, you pay the SSTORE toll. These two opcodes completely dominate state change costs. They are for sure the primary villains behind high gas fees, and learning how to avoid them, that's going to be your new superpower.
So, the million-dollar question is, how exactly do we bypass these expensive storage tools? I really want to challenge you to think about this. How can we reduce distinct storage rights? How can we cache data locally to avoid paying those repeated reading fees? Because if you can crack this, you can drastically cut the cost of your smart contracts.
All right, Section 3, setting up the environment. To test our theories, we obviously need a lab. By using a local network, we can measure gas deterministically without burning any real ETH, which is always nice. Let's build our testing foundation. Go ahead and open your terminal. First up, make a directory called gas-drills. Second, initialize it with npm init-y. Third, install hardhat and the ethers library. And fourth, just run npx hardhat to create an empty configuration file. Boom. This gives us a completely controlled measurement space.
Now, to build this isolated test environment properly, we need a really precise file structure. So our contracts directory is going to hold drillbefore.sol, which is our unoptimized baseline, and drillafter.sol, our optimized variant. Then our scripts folder will contain our Node.js measurement script, gas_drills.js. And finally, our output folder will house the gas results JSON file. Keep it neat, keep it structured, right?
Section 4, before and after code. It is time to put our unoptimized code under the microscope right next to its optimized counterpart so we can isolate two very specific patterns.
Check this out. Our unoptimized drill before contract is, frankly, bloated. It reads the exact same storage slot multiple times, triggering repeated SLOADs. It executes multiple distinct SSTORE operations and stores flags completely separately, just wasting space. But our drill after contract, oh, it is beautifully slimmed down. We cache storage reads into local variables so we only hit the state once. We combine our math and memory, executing a single SSTORE at the very end. And we brilliantly use bitwise operations to pack multiple flags into a single write. It's just elegant and highly efficient.
Section 5, measuring the gas data. Look, writing elegant code is great, but as scientists, we actually need to prove our theories. We have to run our gas drill script to get the hard numbers.
Here's exactly what our Node.js script is doing behind the scenes. First, it compiles both smart contracts. Then it deploys them to hardhat's built-in network using default accounts. Next, it invokes our targeted functions, passing identical inputs to both of them. And finally, it captures the receipt.gasUsed property.
This is absolutely vital because gas used captures the actual transaction cost after execution, automatically rolling up the intrinsic and runtime costs for us.
And here we go. The resulting machine-readable JSON output proves our optimizations worked. We capture the timestamp, the contract name, its deployed address, and crucially, the gas used. The unoptimized code hit over 123,000 gas, but the optimized code down to just under 99,000.
I mean, that is a dramatic drop in gas usage. Just because we cached our storage reads to reduce SLOADs and combined our flag writes to reduce SSTOREs, we shaved off a massive chunk of the execution cost. When your users are paying real money for these transactions, this exact difference is what separates an amateur contract from a true professional one.
Section 6. Next steps and capstone. Let's wrap up our experiment and look at how this prepares us for the next stage of the curriculum. I want you to burn this quote into your memory. Seriously, this is the golden rule of Ethereum smart contract development. Never assume an optimization helps until you measure gas used under controlled conditions. I've seen it so many times. Sometimes what looks like an optimization in Solidity actually creates more overhead for the EVM. Rely on empirical data, never just on speculative coding.
Let's quickly recap the key takeaways you can apply to all your larger contracts from here on out. First, train your brain to think in opcodes per logical step. Second, always cache those expensive storage reads into local variables. Third, minimize distinct storage writes by combining and packing flags. And fourth, say it with me, always measure your results deterministically in an isolated environment.
You did great today. Now be sure to keep your script and JSON results handy because these artifacts feed directly into our upcoming optimization workflow and capstone preparation lesson. We are going to automate all of this into a massive multivariant pipeline. And hey, to learn more about this subject and completely master Web3, you absolutely have to visit forge.college. It's the best resource out there to take these concepts to the next level.
So, as we close the lab doors today, I want to leave you with this final thought. You've conquered SLOAD and SSTORE, but what other hidden opcodes are secretly draining your contract's gas right now? Keep questioning, keep optimizing, and I'll catch you in the next explainer.